You ever just look at a skyscraper or a massive bridge or even the road you're driving on and think, how how did they even build this? It didn't just appear. It didn't start with a single shovel. It all started with a plan, a blueprint. And today, we're going to deconstruct that blueprint. We're looking at the civil engineering syllabus, not as some boring list of exam topics, but as the actual recipe for building our entire physical world. So, let's get into it.
And this quote right here, this is our North Star for this whole explainer. It's the entire point. This isn't about cramming your head full of formulas. It's about seeing how that abstract math on a piece of paper becomes a tangible, real-world bridge that you can actually drive your car across. It's all about the application.
So where does a project actually begin? You might think it's on a dusty construction site with a bulldozer, right? Nope. It starts right up here, in the mind. Before anyone breaks ground, an engineer's mind has to be prepped, organized, and ready to go with the right strategy.
Think of this as the engineer's mental warm-up. Step 1, you've got to master the basics from the textbooks. No shortcuts here. Step 2, you take all that complex math and boil it down onto a formula sheet. Step 3, and this one is so important for engineers, you have to learn visually. The rule is, if you can't sketch it out, you don't really get it. And finally, you put all that knowledge to the test against old exam papers to see how it holds up in the real world.
Okay, so the mind is prepped. Now we can finally head to the site. We're on location. So what's the very first job? You have to learn to read the land, to understand its story, its dips and hills, its secrets. And only then can you start picking out the right tools and the right materials for the massive job ahead.
And this all kicks off with surveying. Now, I know it might not sound like the most thrilling thing, but trust me, it's everything. Think of it like this. Surveying is the art of taking our messy, bumpy, three-dimensional world and translating it into a perfectly flat, super precise two-dimensional map. It's the canvas. Without it, you are literally building blind.
So how do they actually pull this off? Well, they have some pretty cool tools. We're talking about instruments like theodolites and total stations that measure angles and distances with insane precision. And they use concepts like contour lines, those squiggly lines on a hiking map. For an engineer, those squiggles are a language. They tell an engineer in an office the exact shape of a hill that's hundreds of miles away.
All right, the site is perfectly mapped. Now it's time for the engineer to switch hats. You're not a surveyor anymore. You're a materials scientist. You've got to pick your ingredients. And here are the absolute staples. You've got cement, which is basically the glue for everything. Concrete, the undisputed modern workhorse. Classic bricks and stone, and of course timber. And the level of detail you need to know here is just wild. It is not enough to just say, let's use stone. An engineer has to basically be a geologist. They need to know its whole life story. Was this rock born in a volcano? Was it squished to the bottom of an ocean for 1,000,000 years? Was it cooked by intense heat deep underground? Because each one has totally different properties. It's just like knowing exactly how long different types of cement need to set.
Okay, let's recap. Our mind is prepared, we've mapped the land, we've picked our materials. So what's next? Now, we go vertical. This is the part where all that planning and all that knowledge starts to become a real physical thing that you can actually see and touch.
Now think about this. On a huge construction site with hundreds of people, from architects to welders, how does everybody stay on the same page? Well, they all speak a universal language, and it's called engineering drawing. It's a mix of old-school principles, like the top-down view and the side view, with the lightning speed of modern computer programs. Even the way things are shaded is a code. It tells you instantly if you're looking at concrete or steel.
The very first piece of the actual structure is probably the most important thing in the whole project, the foundation. This is literally the handshake between the building and the planet Earth. And the choice is pretty simple, but it's crucial. If the ground is solid, you can use a shallow foundation. But if the ground is soft or swampy, well then you gotta go deep, driving massive piles down until you hit solid rock. If you get this wrong, absolutely nothing else matters.
All right, the foundation is in. But what stops the building from just toppling over in the wind? This is where we get into some seriously cool physics. It's called structural mechanics, and it's basically the science of an invisible war of forces. Inside every single beam and column, you have stress pushing and pulling, and you have strain, which is how much the material bends or deforms. An engineer's job is to manage that war.
Which brings us to a kind of scary but unbelievably important question. See, an engineer's job isn't just to build things. Their real job is to know, with mathematical certainty, a structure's breaking point. They have to predict failure long before it could ever happen. So, how in the world do they do that?
Well, this is the brilliant part.
They turn the invisible visible. They use these special diagrams. Now, they have fancy names, but what they really are, they're like X-rays for the forces flowing through a beam. These diagrams let an engineer see exactly where the points of maximum stress are. That way, they know precisely where the design needs to be the strongest. It's this predictive power that is the absolute bedrock of safety.
So, we've built a strong skeleton. But a skeleton isn't a home, right? It's just a shell. To make it a place where people can actually live and work, you need to add all the internal systems, the veins and arteries that truly bring a building to life.
Let's start with that first connection to the outside world, the road. And right away, engineers have a huge decision to make. Do you go with flexible pavement, the black asphalt kind that's cheaper up front, or do you invest in rigid concrete pavement, which costs more now but lasts way longer? That single choice can affect budgets and maintenance schedules for decades.
Now let's head inside. You go to a sink on the 20th floor and turn on the tap. How do you know that water is safe to drink? Well, it went on quite a journey. First, in sedimentation, all the heavy gunk is allowed to settle to the bottom. Then, filtration gets rid of all the smaller impurities. And finally, chlorination disinfects it to kill any germs. It sounds simple, but doing this for a whole city? That's a massive engineering feat.
And it goes way beyond just water. There's this whole hidden world of systems that you only ever notice when they stop working. The ventilation that keeps the air fresh, the simple genius of that little U-shaped pipe under your sink that stops sewer gas from getting into your house, fire safety systems, standing guard, even the acoustics that control noise. These are all called building services, and they're the invisible web that makes a building comfortable, healthy, and safe.
Okay, so we understand the science, the materials, the systems. But how do you actually conduct this massive, complex orchestra of people, machines, and materials all at once? Well, that brings us to the final part of the blueprint, the art of actually managing the whole project.
It all starts with counting. Everything. The process is called estimating and costing, and it's where you figure out the budget before you even start. And every single little thing is measured differently. Concrete is measured by volume, steel is measured by weight, and something like plaster is measured by its surface area. You have to be incredibly precise here, or you're going to run out of money. But money is only half the battle. The other half is time. How do you keep this gigantic project on schedule? Engineers use two main techniques for this. The critical path method, or CPM, basically creates a giant flowchart to find the sequence of tasks where any delay will delay the entire project. PERT is similar, but it's for when you're not exactly sure how long each task will take. Both are about making the project run like a well-oiled machine. So let's pull all these different threads together now. We've journeyed all the way from surveying a patch of dirt to managing these incredibly complex timelines. And when you combine all of it, what you get is so much more than just a building. You get the very fabric of our modern world. And that really is the biggest takeaway here. This collection of knowledge, of material science and physics and logistics and geology, it's not just some list of topics for a test. This is the recipe book. It is the literal step-by-step instruction manual for how we've built our civilization. So I want to leave you with one final thought. The next time you cross a bridge or walk into a skyscraper, just stop for a second. What do you see? Is it just concrete and steel? Or can you now see the blueprint behind it all? The invisible forces being perfectly balanced, the precise calculations, the complex web of systems, and the incredible human ingenuity holding it all together.